What is the slope of line? It's the same wherever on the line. What is the slope of a curve? It depends where we are on the curve. The slope of a curve is really the slope of the tangent line to a point on the curve. Here is a picture. The slope of the blue secant line approximates the slope of the red tangent line. The approximations get better as x approaches a. Think limit. Note x equals a yields 0 over 0. The tangent line to f of x at x equals a is the line through the point with slope m. M equals f prime of a equals limit as x approaches a, f of x minus f of a all over x minus a equals limit as h approaches 0, f of a plus h minus f of a over h. Here is the tangent line of f of x equals x squared at point where x equals a. We have the following. When x equals a equals 1, the slope is 2. The tangent line to x squared at 1, 1 is y minus 1 equals 2x minus 1, or y equals 2x minus 1. The derivative of a function f at x equals a is f prime of a equals limit as x approaches a, f of x minus f of a over x minus a equals limit h approaches 0, f of a plus h minus f of a over h if x equals a plus h. This function is differentiable at a if f prime of a exists. The tangent line to f of x at x equals a is the line y minus f of a equals f prime of a, which equals m, x minus a. Parallel lines have the same slope m. Normal lines have the slope minus 1 over m. We differentiate the function f of x equals x squared to find its derivative, f prime of x equals 2x. The average rate of change of y equals f of x with respect to x over the interval x1 to x2 is delta y over delta x equals f of x2 minus f of x1 all over x2 minus x1, which is the difference quotient and can be interpreted as the slope of the secant line that connects x1 f of x1 and x2 f of x2. The instantaneous rate of change of y equals f of x with respect to x at x equals x1 is limit as delta x goes to 0, delta y over delta x equals limit as x2 approaches x1, f of x2 minus f of x1 over x2 minus x1, which is the derivative f prime of x1 and can be interpreted as the slope of the tangent line at x1, f of x1. Notations that we'll use are f prime of x equals y prime equals dy dx. If we want to take the derivative and evaluate at a, then f prime of a, dy dx, x equals a, dy dx, x equals a. The derivative of the first derivative is the second derivative. F double prime of x and higher derivatives, the nth derivative at x here is a picture. The differential dx is how much x changes. The differential dy is how much the tangent line rises or falls by dx. dy equals f prime of x dx. In contrast, how much the function rises or falls by delta x is delta y equals f of x plus delta x minus f of x. As an example, let f of x equal x squared, with f prime of x equals 2x, and consider a equals 1. And so f of 1 equals 1, f prime of 1 equals 2. From here, we can find the following equations. Tangent line, linear approximation, linearization. If we had dx equals delta x equals 0.5 and x equals 1, then we could find change in tangent line, change in function. So the linear approximation for x squared centered at x equals 1 will give L of 1.5 equals 2. Where derivatives exist, the functions look locally linear. Derivatives do not exist, DNE, with discontinuity, corners, cusps, vertical tangents, and oscillations, since they do not become locally linear. None of these functions have derivatives at x equals 0, so no tangent lines there. If f is differentiable at a, then f is continuous at a. But the converse, which is if f is continuous at a, then f is differentiable at a, is not true. Nuance. Although a derivative might not exist at a point, it might exist at other places. Consider f of x equals absolute value x, and how geometrically f prime of x equals this. Note that two functions could be non-differentiable at a, but combinations of them could be differentiable at a. Consider adding a positive and negative absolute value to get the horizontal line y equals 0, with slope y prime equals 0. Although each individual function wouldn't have a derivative at x equals 0, the sum y equals 0 does. Basic derivative rules. Constant multiple, sum and difference, product rule, quotient rule, chain rule. Derivative rules. The derivative of x to the power n equals n x to the power of n minus 1. The derivative of a constant is 0. The derivative of a constant times a function is that constant multiplied by the derivative of that function. We need to manipulate our function so that the rules apply. Also simplify. Find the derivatives of x squared, x squared root x, x, square root x, and 1. And we have the following. Find the derivatives of 1 over square root x, 1 over x, 1 over x square root x, 1 over x squared. Find the derivatives of 10x squared over 11, 10x square root x over 9, 8x over 9, 8 square root x over 7, 6 over 7. Find the derivatives of 6 over 5 square root x, 4 over 5x, 4 over 3x square root x, 2 over 3x squared. Differentiate f of x equals x squared e to the x, and g of x equals e to the x over x squared. Note that we can't manipulate. Recall product rule. Fg prime equals f prime g plus fg prime, and quotient rule. F over g prime equals f prime g minus fg prime over g squared. We have the following. Sometimes, if we can manipulate, we can bypass product or quotient rule. Consider this. Y equals t cubed x to the power 5 plus t to the power 7 x to the power 9. To find dy d whatever, we treat only whatever as a variable and everything else as a constant. And we have the following.